Hi everyone, so let's move on with unit 1.1. So this is just a recap of what you already know about matter. So the kinetic particle theory states that particles are in constant motion, that matter is made up of particles which include atoms, molecules, or ions, and matter has mass and matter occupies volume. The states of matter, you have to know the properties of the three states of matter. And you need to be able to interpret a heating curve or a cooling curve. So here you have a heating curve. So the x-axis is time and the y-axis is temperature. The temperature of the mixture is going to be monitored with time. So at these points here where you see the temperature rising, so the energy being supplied is converted to kinetic energy, and the molecules in the lattice are going to vibrate more or move more in this region here. At these points where you have these flat regions, we say that an equilibrium is reached. So here we have the solid, here we have the liquid, over here we have a solid liquid equilibrium which is formed. At this point there is no change in temperature. The energy being supplied is used to disrupt the lattice and the particles become more free to move, and here we see that the disorder is increasing. So you're going to have a mixture of two states at this point of equilibrium here. And at this point, all the solid has melted. So you have just the liquid. And when you're heating, all the energy is being used, is getting converted to kinetic energy. So the particles, all the molecules will vibrate faster, and the temperature rises. So when kinetic energy of particles increases, temperature also increases until it reaches the boiling point over here. And at the boiling point, you're going to have a liquid and gas equilibrium. And here again, the temperature will not change because the energy is being used to overcome the attractive forces between the molecules of the liquid. Now note that the unit of temperature, the SI unit of temperature is Kelvin. And for you to convert degrees Celsius to Kelvin, you're going to add 273. And to convert Kelvin to degrees Celsius, you're going to subtract 273. And please note that we do not say degrees Kelvin, it's just Kelvin. Now, this part is called the Internationalmindedness. So it's just looking at chemistry in an international point of view. And as you know, we have a system of naming in chemistry. This is called nomenclature, and this is regulated by the IUPAC, which is the International Union of Pure and Applied Chemistry. So what it does, it ensures that there is consistency when we're naming compounds or when we're using symbols and words, so that you don't need to have any translation from one country to the other. So it ensures that there is consistency in whatever language we're using in chemistry. So let's see some of this language in terms of symbols. So as you know, we have a chemical formula. So you have lots of things that happen that show in a chemical formula. These little symbols are called state symbols, and they show the states that the substance is. So solid, liquid, gas, aqueous, which means dissolved in water. Then you have the symbol of the substance, so CH4, O2, CO2, H2O. These are the symbols of the molecules or the particles. And the number that you're going to see, the number 2, which is subscript here, number 4, which is subscript here. So this subscript is actually showing you how many particles are there in that molecule. So for example, CH4, this actually means that there is 4 hydrogen in a molecule of methane. So CH4 is methane, so there's 4 hydrogen in methane. Here, CO2, it means that there is 1 carbon and 2 oxygen in a molecule of carbon dioxide. So it's actually showing you how many particles there are in that particular substance. And here, the number in front, this is called the stoichiometric coefficient. So whenever I'm referring to stoichiometric coefficient or simply coefficient, I means the number in front here. Now, when there is no number, this is counted as 1. Okay, but we don't put 1. So just to let you know, so if there's nothing, it's 1. Now, this is a chemical equation. And on the left-hand side, you have the reactants. And on the right-hand side, you have the products. This is always like this. And every chemical equation that you write needs to be balanced. Another important part of understanding the symbols is the use of arrows. Single arrow shows that the reaction goes to completion, and reversible arrow, it shows a state of equilibrium, which means that the reaction proceeds in both directions.